All right, here we go. Newton's second laws in 2 dimensions. So we've actually done a lot of this, where, like, for example, you've got a box or something sitting on a thing, and, maybe Roy pushes this way with some force, right? So automatically, because that force is at a weird angle, we got to split this up into 2 dimensions, right? The big distinction is this. When we did these types of problems in the past, what we've always found was that, for example, this one, your net force vertically is 0, so you really only had to worry about your net force horizontally, right? And similarly, we had other problems where, all of your motion would be vertical, and your horizontal forces would cancel out, or whatever. This time, we're going to be dealing with problems where you got to worry about your forces in 2 dimensions, and you might have a net force both vertically and horizontally, okay? But it doesn't actually make it that much harder, all right? So here's a simple example. All right, so in this first example, it says, Roy kicks a football of mass m up into the air. At the instant the ball is at the top of its path, air resistance exerts a force of magnitude 2m. Find the magnitude and direction of the ball's acceleration at the top of its path. All right, so here's the deal. So the ball, gets kicked up into the air like this, right? And so the idea is, when it gets to the top of its path, what do we know? Well, let's see. At the top of the path, I know that my Vy is 0, which means my velocity is just the same as whatever my Vx is, this way, right? So V, right? Okay, so at that instant, what forces are acting? Well, we know we've got gravity pulling straight down, right? So that's going to be, I'm going to actually use 9.8 m this time. 9.8 m negative, right? And I guess we might as well be a little more specific here. This is in the j direction, right? So the force of gravity is negative 9.8 times the mass in the j direction, all right? And there's air resistance. Now remember, air resistance always resists velocity. So if the ball is moving to the right, air resistance is to the left. So that means I can put in my air resistance, force of air. We'll eventually begin calling that Fd for drag force. All right, and that's going to be negative 2m in the I direction, right? Okay, and I think that's it. Those are our only 2 forces, right? You got gravity pulling the ball down, air resistance pushing the ball back. So we can find our net force, right? So our net force on the ball should be the force of air resistance plus the force of gravity. Now remember, this is vector addition. So it's not as simple as just 2 plus 9.8. It's this. Net force is negative 2m in the I direction plus negative 9.8 m in the j direction. And so now I can find my acceleration if I want, right? Because acceleration is net force over mass. So if you take this whole thing here and divide by m, the m's cancel out, and so you get negative 2I minus 9.8 j meters per second squared, right? So there's our acceleration, right? And then the question actually technically asks for the magnitude and direction. So at this point, you'd have to draw your acceleration vector. So our acceleration vector is going to be, well, let's see, we got negative 2I, negative 9.8j. So here's our acceleration vector, right? So you can do the Pythagorean theorem and find the magnitude, and then find your direction. Okay? So that is that. Acceleration in 2 directions. Okay? So, but at the root of this, I guess the main thing that I want to make sure that you understand is you're almost always best to split everything up into components right from the start. Okay? Now you'll see there will be exceptions, but if the problem is, even a little bit complicated, I think that working in components is going to be your best bet. Okay, so that is the deal there. All right, so this next example, I think, sort of illustrates that a little bit better. All right, so here we've got a 2.5 kilogram box of tiny unicorns sitting at rest on a frictionless floor. Al, Bob, and Carl are fighting over the box. Al pulls the box with a force of 20 newtons. So let's do this. Al pulls with 20 newtons at 30 degrees south of east. Bob pulls with 15 newtons at 20 degrees south of west. And then Carl is there. Okay. His job is he's got 2 seconds to get the box moving at a constant velocity of 10 meters a second at 60 degrees south of east. All right. So he's got 2 seconds to cause acceleration. And then after those 2 seconds, it needs the velocity to be constant. Okay? So during the acceleration, let's see what's going on. Well, what do we know? We know that our initial velocity is 0. We know that we've got a time of 2 seconds. And at the end of that time, we want our final velocity to be this, 10 meters a second at 60 degrees south of east. So I would say take that velocity and split it up into components. All right, this is not the only way to do it, but I do think it's probably going to be the easiest way to do it. So if you take that 10 meters a second at 60 degrees south of east and you split it up into components, you end up getting 5I minus 8.66 J meters a second. Okay. So now what I can do is I can use that information. Remember, these are vectors, right? So I can find my acceleration like this, right? So let's see. So I'm going to get this final velocity minus 0 divided by my time. So plug in your numbers and you end up getting 2.5I minus 4.33 J meters per second squared. All right, and the question is about force, right? Well, I just found my acceleration, so probably a good next step would be to find the net force. So our net force is mass times acceleration, right? So look, we know our mass is 2.5. We just found our acceleration, so just multiply all of this by the mass of 2.5, and you end up getting a net force of 6.25I minus 10.82 J newtons for net force. All right, so that's what we need to happen during the acceleration, okay? So now, what else does it tell us? Well, let me do this. I'm going to buy myself a little bit of space here. All right, so now what we need to do is we got to figure out what's going on with Al and Bob. So the problem tells us that Al pushes with 20 newtons at 30 degrees south of east. So the force of Al is, if we split it up into components, 20 newtons at 30 degrees south of east, that's the same as 17.32I minus 10J newtons. All right? Similarly, we know Bob's force here. So the force of Bob is, we know it's 15 newtons at 20 degrees south of west, so that's negative 14.10I minus 5.13 J newtons. All right. And the question is, what does Carl have to do? And while it's accelerating, the idea is we want this net force to be this thing, right? 6.25I minus 10.82 J. All right. And the idea is everything here has to add up, right? So these guys need to add up. And these guys need to add up. Okay, so solve this, and you'll discover that Carl's force, while it's accelerating, has got to be 3.03I plus 4.31 J newtons. So he has to do that for 2 seconds. Okay, and then let's see, if this will let me do this. Okay, so this is during the acceleration. So for the first 2 seconds, this is how much force Carl should use. All right, then he wants the velocity to be constant, right? So that's going to change how much force he needs. And the idea is now, to make the force constant, we need our net force to be 0, right? So now you basically repeat this process and you go, all right, well, now my net force has got to be 0. So during the first 2 seconds, then Carl needs to exert this amount of force. And now that everything adds up to 0. And so if you do that, you get negative 3.22I plus 15.31 J newtons. Okay, so for the first 2 seconds, he's going to exert this much force. That'll cause it to get up to the velocity it needs. Then once it's at the velocity it needs, then we exert this force to keep the velocity constant. Okay? All right, finally, last example. All right, so now we've got a 4-kilogram box of jelly beans sitting on a warehouse floor. All right, so the coefficients of static and kinetic friction are 0.5 and 0.4. Roy wants the jelly beans to follow this path right here, okay? So that, notice, remember, R is position, right? So the I component represents the X, and the J component represents the Y, right? So we want the jelly beans to follow this path. So there's my R. All right, where T is in seconds, R is meters, and then we're going to have I and J be east and, dang it, I did this again, east and north, right? So I is east, J is north. All right, so assuming the box is currently at rest, so in other words, our velocity is going to begin at 0, and it's at this position to begin with, which if you plug 0 in up here at t equals 0, it gives you negative 2I. Okay, so basically it's just telling you that it's starting in the right position for this to work. All right, so how much force should he use? All right, well, let's see. So it looks like the position is a function of time, right? The position is a function of time. That means there's velocity, and that velocity may or may not be constant, okay? So here's what we know. We know that the position at time t is this mess. 6t squared minus 2 in the I direction, minus 8t squared in the j direction, okay? So if I take the derivative of position with respect to time, that gives me velocity, right? So we can take our derivatives component-wise. So this is going to give me my velocity at time t. So the derivative of this, let's say you're going to get 12t minus the derivative of 2 is 0. So my velocity in the x direction is 12t minus 16t in the j direction, right? So notice the velocity depends on the time, but the idea is it's going to be kind of proportional, right? So at any given time t, my velocity is going to be 12t horizontally. Oops, do this again. My velocity horizontally is going to be 12t. My velocity vertically is negative 16t. And so my velocity here is, well, I guess you could do Pythagorean theorem here. I'm pretty sure it actually gives you 20t. All right, but the point is, this direction is going to be fixed, isn't it? Because, you know, if you do whatever inverse tangent of 16t over 12t, the t's cancel, right? Okay, so it looks like the object is traveling in a straight line. And in fact, let's do this. So my angle is 16t over 12t. Oops. And it gives you, I think it's like 53 degrees. What's my work? 53 degrees. Okay, so that's the direction that this thing is always going. All right, and the moral of the story here is, remember, the direction of motion is determined by your velocity vector. Okay, so my object is always going this way. All right. Now the question though isn't about velocity. The question is about force, and the force is going to be dependent on acceleration, or I guess technically the other way around, right? So let's take another derivative. The derivative of velocity with respect to time. I guess I should be putting vector hats on all of these. So that's going to give me my acceleration as a function of time. So take the derivative. Derivative of 12t is 12 minus 16. So my acceleration is in the same direction as my velocity, right? In other words, it's just going to go this way faster and faster and faster, okay? So that's my acceleration as a function of time. All right, so let's find our net force now as a function of time. So my net force as a function of time, as a vector, is mass times acceleration. So I'm going to take this acceleration and multiply it by this mass. So multiply by 4, and you get 48I minus 64J newtons. So that's my net force. All right, so the goal is we need our net force to be that. Now, let's think about what's going on here. What other forces are there? So here's the box of, what are they, jelly beans, right? And we know that we need our net force to be, you know, kind of off this way, right? At that 53-degree angle that we figured out before. All right, so what other forces are there besides Roy? Well, oops. Oh, well, that's not what I was trying to do, but it'll work. No, well, all right, let's scroll up. Here we go. So the only other force is friction. But remember, kinetic friction always acts in the opposite direction of the velocity, just like air resistance in that last example, right? So let's see. So I know that I want my net force to be this way. This is a little bit, well, here, let's do this. So Roy should probably push in the direction of the net force, right? And the idea is friction is going to act in the opposite direction, right? Because it's going to oppose the motion. And so these two forces need to add up to give us our net force, right? So I think at this point, what probably makes the most sense is, let's do this. Let's find our force of kinetic friction, okay? So everything that we're doing here is top view, right? North, south, east, and west. So for friction, it's going to depend on gravity and normal force, which are sort of pointing in and out of the board, respectively. So let's really quickly do a side view. So here's side view. Gravity is pulling down with a force of 4 times 9.8, so 39.2 newtons. There's a normal force, also 39.2 newtons. Roy is going to be pushing this way with a force of something, and we can find our friction, right? So that's going to be our coefficient times our normal force, right? So 0.4 times 39.2 gives you 15.68 newtons. And so the question is, what does Roy's force need to be? Well, let's do this. If you find the magnitude of this, just by doing Pythagorean theorem, it turns out to be 80 newtons at 53 degrees south of east. Okay, so that's my net force. It needs to be 80 newtons. So if the force of kinetic friction is, what did we just get, 15.68? Let me do this in a different color. So our force of kinetic friction is 15.68 newtons against the motion. Then Roy's force has to be big enough so that I get a net force of 80. So what number minus 15 is 80? 95.68 newtons. So there's your answer. Roy's got to push with 95.68 newtons at 53 degrees south of east. Okay, because the friction is going to oppose the motion. It's going in a straight line, so the friction is always going to go in the opposite direction of the force. So there you go. Two-dimensional motion. Boom. How long was that? Under 20 minutes, I rule. See you in class.